Okay, so we start the class, and as I mentioned in that last class, we always analyze the data pretty short, right? Just maybe a few seconds data. So today we will move to another topic is the power spectrum density estimations. Okay, and actually these methods is very widely applied to the data are quite longer. Okay, so how longer the data? So maybe the data length is maybe a few days or the 1 month or the 1 year. 1 year. So the data, if your data is quite longer, so we need to use the power spectrum density analysis to deal with the time frequency map. Okay. So today our exercise, I provide the data on the field. So as the map showing here, you can see the major rivers here is the Zhenwen rivers. Okay, where is located at the southern Taiwan, the Tainan cities. And you can see there is another tributaries, Hodan rivers, will supply additional water into the major rivers. And our data is from the seismic sensors. So we put the seismic sensor on located here as the triangle showing here, just the right bank of the river channels. And today we also plot the time series associated with the water level. So we should have the water gauge, right? So we put here is the LiDAR's water gauge located here. So this point will provide the data from the water level variations with the different times. So today we only pick up the two data sets. The one data is from the triangle. We put the seismic sensor. So the sensor located here record the seismic signals data. And there is a water gauge stations. So we have the water level data from this point. Okay? And then we just make the comparison between the water level and the seismic signals, and you can see how correlations they are. So the upper panels, I just plot the water level, and then you can see the time dimensional are quite different compared to our previous class. The data is quite longer because you see the unit here is hour. So every 24 hours is per day. So there are 4 days data. Okay, and I just try to analyze the 4 days data with the power spectrum density analysis. So you can see the color bar showing here, the label are different compared to our previous class. Here I put the label is the PSD. This is, I will teach today, the power spectrum and density. And we call that the PSD. And then you can see the units of the PSD is the meter per second square per hertz. Okay? And I use the dB unit here. So if you don't know anything, but you can see, just make very quickly take a look, and then you can find out some relationship between the PSD and the water level, right? As you can see, this water level is quite flat. So you may see some strong signals on the map, but there are no correlations. But if you focus on here, that's very stronger PSD values are consistent with the higher water level stage. So maybe the seismic ground vibrations caused by the water level and you can see maybe the mechanism is when the water flowing and will generate some ground vibrations recorded by the seismic sensor here. Okay, so this is what we need to do today. So the quite different idea compared to our previous class. The idea is because the data are quite longer, so we cannot use directly the method teach before. So we can only apply the method teach today is the power spectrum density analysis. Okay, especially for the longer data, like the example showing here is a 4 days data. But our previous class, we only analyze some data are quite shorter, maybe just 40 seconds or 60 seconds or 100 seconds. So the time scale are quite different today. Today we analyze the data longer than 1 day. And actually we use the 4-day data to do the time frequency analysis. OK， 所以我们今天跟之前很大的不一样是，这是我们第一次去分析，就是比较长时间的资料。以前我们在前面几堂课，不管我们举例了什么范例，都是那种几秒钟，而且可能按一下 Enter 就结束了，然后大家大部分的错误都是在可能 coding 打错 ，L 打成 I 打成 L，O 打成0，0打成 O。那今天我们比较不一样的是，那正常我们在河川里面要使用的其实是长时间的资料，我们看的是1天、2天，甚至是1个月。那如果是这个样子，我们要用怎么样的方法去做一样的时频分析，可以达到一样的效果 ？OK， 那我在这里秀了很简单的案例，就是我们今天唯一要完成的一张图。那你可以看到，其实在这里很红的地方，刚好好像就是在高水位的时期。那在这个相对比较蓝、比较低背景的地方，好像就是在低水位的时期。虽然我们稍微可以看到这里有一些很奇怪的条状的 energy， 好像集中在这里，可是它跟水位好像没有关系，因为基本上水位是没有什么在动的，可是它有一些强弱的变化。那这个讯号我可以直接告诉大家，由刚才上一张 map 你可以看到我们的车站旁边有一座桥。这个就是每天白天的时候，桥上面有车子在经过，它会有一些共振的频率，会让这个仪器收到。所以这个对我们来讲非常正常，就是基本上我可以监控到底谁偷偷的经过这座桥。Okay, so as I mentioned here, you can see some strong signals are not correlated with the water level vibrations. Because we can see the level didn't change, but there are some strong signal vibrations. So I can say that the source caused by the strong energy here is caused by the bridge vibrations. When we have the traffic and some car traffic go through the bridge, and we will see some oscillations frequencies caused by the bridge. Okay. So the idea is what is the power spectrum density, and how can we estimate the values directly? Okay, so I just copy paste the one PDF file right by me. You can see I upload details power spectrum density analysis on the E3 website, and I don't follow the material as I show in here because you cannot understand. But I just highlight some important ideas why we can do power spectrum analysis. Okay, so the idea I go back to the bigger ones from the PDF file. So this is the flow chart today, and when we do the power spectrum estimation analysis. So the AKS is our time series data. When we put into the black box, like here, I show in here, and we can do some output Y functions. So what the response in here is like the Fourier transform. Because we put the time series and we will have the output data with the spectrum amplitude as function of the frequency. Okay, so this is like the Fourier spectrum amplitudes, and we just focus on some specific frequency. Like I highlight F0 here, and this is our center frequency band, and we can control the bandwidth of the our data. Okay, and then we have the spectrum amplitude for specific frequency with a bandwidth b, and then we can calculate the square of the spectrum amplitude and do averages. And finally, I need to divide the result by the bandwidth, and then this is we call that the power spectrum density. So where is the power? Where is the density, right? Why can we call that is the power spectrum density? So I can write down some hint, because maybe we have the XN, and we can do the FFT, maybe the fast Fourier transform. So we can have the Yn. Actually, the Yn is the spectrum amplitude as function of the frequency. And here we can pick up the frequency centers like the F0, and we need to decide the frequency, the bandwidth. So we have the bandwidth, the F1 start to from F1 to F2. So this is the bandwidth of the frequency. And then after we have the Y spectrum amplitudes, and we can compute the square. So this is we compute the square, okay, and do some averages. So here we didn't know why we need to do average and how can we do that. So I put the question mark here, but we know that when we talk about the square, some amplitude we compute the square. You should know that is the power. Okay, so because here is the square, so we can call that is the power. And what kind of the power we have here is the spectrum. So we have this is the spectrum. So why we call that is the power spectrum? Because we take the square is the power, and here is the spectrum. So when we calculate these items, we call that the power spectrum, but we don't have the density. We don't have the density. So how can we have the density? So the next step, we already have the power spectrum, and finally we divided the square functions by the bandwidth here. So we divided the bandwidth. So after I divided the bandwidth here, so we can call that totally this is the density. Okay? Because I divided, initially I just compute the spectrum amplitude powers for the center frequency with the frequency band. And finally, I divided the frequency band. So that will be the density. Okay? So the idea, we call that the power spectrum density today is the power is a square. And the spectrum here, because we compute the time series, apply the Fourier transform, and we got the spectrum amplitude. And then finally, we divided the power spectrum with the bandwidth. So we call that the density. So we have the power spectrum density for specific frequency centers, F0. OK， 所以概念很简单。如果你都不知道数学，可是你大概看公式跟流程图，你可以理解什么叫做 power。我们不管在算什么东西，只要取正负值的次方，通常我们都会说跟 energy 有关系。那 energy 不就是一种 power 吗？那只是 energy 是有时间单位的，那它就会变成 power。OK， 那 所以你只要看到平方就跟 power 是有关系，可是你是什么东西的平方？你本来是傅立叶的正负谱的平方，所以你就会有 power 的 spectrum。可是这里根本没有所谓的 density，density 不就是多少，比如说多少东西，或多少面积，或者多少秒分之什么东西才会有密度的概念。所以在这里我们就最后把它的平宽再除回来，那这个东西就回到 density 的概念。So as I just highlight some important things, when we see the square here, and we can thinking the physical meaning is the power, because we take some amplitude square. After, and what kind of the amplitude I compute the square. This is the spectrum, the Fourier spectrum. So after I compute the square and these items, we call that the power spectrum. But until here, we cannot call that the density, because we didn't divide any normalization factors. So after here, I divided the bandwidth, and we can call that the normalization factor here. And finally, after you divided the bandwidth, and we can call that the density. So all of the flow chart, and we have the final output, and we call that the final one. Here is the power spectrum density, especially for the frequency center x0 here. Okay. So we go back to see the another PDF file, and the PDF file just summarize the background knowledges and brief introductions about the power spectrum density analysis. So we can directly skip the sentence shown on the first page, and I only provide you some knowledges, and so we follow the equations as I show on the second page. So the first one, you have the time series data, and then right now I only focus the 1 hour's time series data. Okay, I only focus the 1 hour's time series data. So how can I have the 1 hour time series data here? So you can go back to see the figures. So today we have the 4 days data. And for each data, I initially is from the 1 day time series. Okay, I have the 1 day time series, and I will do some cut. And I will cut the data into the 1 hour segments. And the 1 hour segments with the 50% overlappings. That indicate here is the 1 hour signals. And here is the 1 day signal length. And I cut the 1 hour data. And this is our segment 1. And the second segments here, you can see the time shifting in here because I allow, this is my first segment windows, and the first segment window is the 1 hour. And I allow the second time window with the 15% overlapping. That indicates the second window here. Okay, the red line is the second window. And inside regions here, we have the 15 overlapping. Okay, that indicates from the first window move to the second window, I only move the half hours because the one window's the length is the 1 hours, and I allow the percentage overlapping. So the second window will only move the 0.5 hours to the next window. Okay? So the window, I can decide many windows with the 1 hour's length. So, but the totally input data is 24 hours, 1 day data. So I cut the 1 day data into the 1 hour segments. And each segment with the 50% overlapping. So that means this is the first time window, and I move to the second time window. The moving step only the 0.5 hours. So you can compute how many segments you have for 1 day data. So totally, as I figure showing here, I have many 1 hour segments. Many 1 hour segments, and totally I have the 47 segments with the 1 hour's length. Okay, so you should keep in mind. Remember, we have the 1 hour window length, and the 1 hour usually we call that the time window for the long segment. So here the 1 hour. This is data length for long segments. Okay, and totally we have the 47 segments, and our input data, the input data is 1 day. Okay, and 1 day we have the 24 hours, right? So the 1 hour is our long segment windows, and for each 1 hours, I also cut into for each 1 hours, I also cut into the 15 minutes. Okay, so difference for each 1 hours, I also cut the 1 hour's time series into the 15 minutes segments. But right now the difference here, the overlapping is not the 50%. I change it to the 75% overlapping. So what are the meanings? So right now the difference here, I know that this is my first window, and the window length here is changed to the 14 minutes. Okay, and the second windows I allow the 15. I allow the 75% overlapping. So the overlapping area here is the 75%. So let's indicate here, you need to know the moving windows here is the 3.75 minutes. Because I would like to move to the next windows, but I only move the 3.75 minutes. Will allow the overlapping area in here is the 75%. Okay, so here I call that the 15 minutes window is the time window length, but for the short segment. So the 15 minutes is the data length, but for the short segment. And you can see, because you cut the 1 hour's data into the 15 minutes small segments with the 75% overlapping. And finally, you can compute how many short windows you have. So finally, we have the 13 segments for the short window. Okay. So for these windows, we have the 13 segments. Okay. So the idea in here, you will know that because our data is quite longer, so before we do analysis, we should cut the data into small segments. And then for each 1 hour, I cut into the 13 segments. And then you can rewind some ideas. I compute the average on the figure 1. So as I remember, I mentioned the question mark here. Here I do the average. So how can I do the average? That's because I cut the 1 hour segments into the small segment windows. And totally I have the 13 window lengths. So I can compute all the results from the 13 windows and take the average. OK， 所以在这里其实有点复杂，不过你可以想象到的就是，我们分析的时间很长，不可能直接丢进去分析，所以统计学家跟数学家他们就发明了，那我可不可以用小段的时间窗口也代表整段的那种物理的概念？所以他们就发展出，我把24小时先切成47个1个小时的视窗，然后我针对这47个的1小时的视窗，再把1小时切成13个15分钟的视窗，那我就可以去算这13个算出来的结果的平均，代表的是这1个小时的表现。那可是这个小时会被移到下一个小时去，这中间会差0.5个小时。1个小时的窗口会跟下一个小时的窗口差0.5个小时。那为什么会这个样子？是因为我决定长的时间是1小时，短的时间是15分钟，就会有这样子的组合结果。所以代表使用者可以自由的去调整，你长要是1小时，还是2小时，还是3小时都可以。那你短的要是1分钟、2分钟，还是5分钟也都可以。那为什么我今天在这里讲1小时跟15分钟？代表我们今天的练习就是要这样子做。OK， 所以今天我们就会发现，那我们用1小时的窗口，可是我们的时间间距为什么是0.5个小时？原因是因为我移动窗口就是每0.5个小时会有一个答案，每0.5个小时会有一个答案。那每1个小时的窗口，我会算到13个15分钟的小窗口的平均，代表这1个小时的结果。那是因为什么有13个？是因为我假设我的小的窗口是15分钟，所以一旦你去动了刚才这里黑色的1个小时，你去动了这里黑色的15分钟，其实个数就会不一样了。你有的10窗口的个数就会不一样，所以我把公式都写在这里。其实你只要稍微带公式进去，你就可以任意去计算。如果是不同的时间长度，你就会有不同的窗口个数。OK， so the idea is here we think that for the longer data we cannot do analysis directly. So before do analyzing, we should cut the data into the small segments. But right now the idea we have 2 different data lengths. The first data length is the 1 hours. And for the 1 hour's data length, we have the 15% overlapping. So each 1 hour's time windows, the moving step is the 0.5 hours. Okay? And for 1 hour's data, I also cut into the smaller showtime windows. And I decided to use the 15 minutes length for the showtime windows. But right now the different compared to previous one, I used the 75% overlapping. So the moving step for the small window size is the 3.75 minutes. Okay? So totally, you just keep some important parameters in mind. Is the 47 segments for 1 hour, and the 13 segments for showtime windows, but the length is 15 minutes. Okay, so if I go back to the PDF file, and then you should, there is a step summarized for the power spectrum density analysis. So first one, we have the time sequence, and the time sequence is the 1 hour data. And so totally we have the K segments, okay? And I cut the 1 hour data into the K segments. So here the K, if the 1 hour data and I decided the show time window length, I use the TLS indicate the show time window length. Okay, this is a short time window length. TLS is equal to the 15 minutes if I assume the show time window length is the 15 minutes. And then here the K should be the equal to 13, right? We just follow the figure 2. We know that if I decided the TLS is the 15 minutes, and we have totally 13 segments. And then for each segment, we have the endpoint, the endpoints number, okay? Because here we have the n, and the segment 1, the point is start from the 0. You can see start from the 0, and the second is 1, and the final point is the n minus 1. That indicates for the one segment, the data length, the points is the n points. Okay, and we have the several K segments, and we can capture the different time series data. Okay, so for the step 1, here is the step 1. This is the step 1. Okay, the step 1 just cut the data into K segments, and we assume that each segment, in case in our exercise today, we assume the overlapping is the 75% overlapping. Okay, so here this is assumptions we use today is the 75%. Okay, so we have the 13 segments, small segments, and we move to the step 2. We move to the step 2. And for each segment, I compute the Fourier transform. So you can see here, I compute the Fourier transform, and I will have the spectrum amplitude result. Okay, so this is our input time series data, and this is the window function. And the window function here, usually we always use the bus car functions. The bus car functions. We just cut off the window, and this is continuous time series data, but we only cut off the one significant windows to do the Fourier transform. And this is the Fourier transform operators. And you can see the frequency and the time information here. Okay, so you can see here we have the Fi. This is the Fi, and this is the time Tn. Okay, and how can we decide the Fi? The Fi is indicated the frequency point. So we have the I and divided the m delta t. The m is the total data points for each segment, and the delta t is the sampling interval. So m multiplied delta t is the total length of the data. And as I mentioned, the total length over y is indicated the delta f. Okay, and this is, I write down here, this is the Fi, and multiply the Tn. And you can see the Tn I defined here. We have the delta t, and we have the different n points. So this is indicated different time step. Okay, so we can put the n delta t here. So you can cancel out the sampling interval, and finally we only have the capital N and the small n and multiply the I. So you can see the result showing here is as the same as I write down in here. Okay, so the step 2 we just apply the Fourier transform and then we compute the spectrum amplitude already. Okay, and what is the step 3? So here is the step 3. And we would like to compute the power. So here we have the power spectrum already because this is a square. You can see the equation there is a square. So we compute the power square. Okay. So after I compute the power, the equation on the left here, we can call that is the power spectrum. Okay, and here you can see we have the W here. The W is equal to sum of the window function square. As I said, the window function always is the bus car, and I assume the amplitude of the bus car here is the 1. So this item summations, this is sum square of the window function. Finally, will equal to the n. So this is W will equal to the n. So we can rewrite the equation. We can rewrite the equation here. Pk I frequency will equal to the n over 1, and the spectrum power here. Okay. So I just replace the W by the capital N here, and the N is the total data points for each segment. Okay, so the step 3 just compute the power spectrum because we can see the power here. Okay, so follow the step 1 to the step 3. Finally, we already have the power spectrum. And the final step, we should divide the bandwidth of the frequency. So we can move to the 4th step here. This is step 4. And then you can see the step 4, we should a step 4 and a step 5 here. Finally, we can compute the bandwidth B here. As we know, the bandwidth is the delta F. So previous equation here, we should divide the delta F, and the delta F Pk I frequency divided the delta F, and but the delta F in here is the n multiplied delta T over 1. So that's equal to the Pk I frequency multiply the n and multiply the delta T. And then you put the Pk I frequency in here. So you have the n over 1 and the k I frequency power multiply the n multiply the delta T. And you can cancel out the delta capital N. So finally, you know that the power spectrum density will equal to the xk I frequency multiply the delta T. So the items I write down in here, this is our power spectrum density, but only for the one segment. But totally we have the 13 segments. So we can compute the average. We can compute the average for the total segments. Okay, so the 步骤1，时间序列进去傅立叶转换，转完以后我取 square， 然后取完 square 以后我除上所有的 频宽，那这里的频宽就是我的 delta F， 就是我频率上的解析力。那1个小时我可以切成13个短时窗口，所以我真正取平均是对13个加起来以后去取平均，那就变短时窗口的平均。那我算出来以后就得到这个 PSD 是为了特别的频率，而且只有在这个时间点的特征这样子。Okay, so we have summarized the 5 steps, and the first one step we just compute the time series data input to the Fourier transform. So we have the output spectrum amplitude, and then we calculate the square of the spectrum amplitude to have the powers for each segment. And then for each segment, we can also divide the delta F with the frequency resolution. We can call that the bandwidth. And then totally for 1 hour segment, we have the 13 small segments. And we take the average, and finally I can output the power spectrum density. Okay. So this is just a very quickly introductions. And the second question is, after we compute the power spectrum density, what's the unit of the power spectrum density? So I just write down some important idea, but you can only say, notice that the U is our input data, the unit. So if my input data is ground velocity, so this is my input data, is the ground velocity. Okay, this is the input time series data. The unit is the ground velocity. So I know that the ground velocity, the dimensional is the meter per second. Okay, so what's the unit of the power spectrum density? You see that I highlight here. The unit of the power spectrum density is the U squared per hertz. Is the U squared per hertz. So right now the U I use in here. This is my unit. So this is my units of the input data. And the power spectrum dimensional. So we have the power spectrum density dimensional will equal to the U squared per hertz. And right now my U input data here is the meter seconds. So we can have the square and the divided the hertz. So the power spectrum density, the unit is depend on your input data. If your input data is the velocity and the dimensional is the meter per second. So after you compute the power spectrum density, the unit will equal to the meter per second square divided the hertz. Okay, so if you have remember as the result I show in here, the color bar I show in here, the unit is the meter per second square per hertz. Okay, so that's depend on what's your input data. If my input data is the velocity, and after I compute the power spectrum density, the unit is the unit square per hertz. 哦，这个很重要，就是当我们在做这些东西的分析的时候，未来你自己在做研究分析也是一样，不是做这类的分析，就是你在画一张图的时候，如果你有数字，不可以没有因次。你有数字就不可能没有因次。那既然你写出了数字，你就一定要提供它的因次。大部分的人做很多分析，如果他不知道是怎么算的，但是会有数字，他就真的会画了一张图，然后没有，不跟我们讲那个数字到底是什么，那就会让人家没办法理解说，那个东西到底是什么物理意义。所以我在这里特别强调，如果我们在做完 PSD 分析以后，物理量的单位就是你本来输入的时序资料的物理量的平方除上赫兹，那就是算完 这个 power spectrum density 的单位，物理量的单位。哦，那为什么我这里上面会写一个 dB？ 因为我把算出来的数值取 log 再乘上10。大家应该有印象 ，dB 是声音的定义。那你把声音的强度取 log 以后，但是要乘上20才变 dB。那我们在这里定义的是乘上10，取 log 以后乘上10，那我定义它是 dB 这样。OK。So the idea is when we make the plot and we show out the color bar and there are some numbers. So we can't show the unit. So we need to understand how the units, how the dimensional after we compute the power spectrum density. So that's I highlight the idea how can we determine the dimensional of the power spectrum density is the input data units squared per hertz. Okay, it's a unit input data square and per hertz. Okay, so that's the final chapter section here. You just go through summarize the interpretations. How can we compute the power spectrum density? So I just skip these portions and then we will move to exercise and try to do some coding and after we do the analyze codings and then we will do the plot. Okay, so I just summarize the idea for the power spectrum density. So the idea quite simple because we are analyzing the longer data. So we can't just put the longer data directly into the program because the computational time is quite larger. So before we do analyze, we should cut the data into the small segment. So for the user, I'm the user, and I only need to decide the two time window lengths. The first one, we need to know the longer window length. And the second, we need to decide the shorter window length. So in here, in the today exercise, we will use the 1 hour as the longer window length. And 15 minutes for the shorter window length. After I decided the longer and the shorter window length, and I will decide how many segments I have. For example, 1 hour per day for the per day, 1 day data. Totally, I have the 47 segments for the 1 hour data. And for each 1 hour data, I can cut into the 15 minutes segments. And we will have the 13 segments for the shorter window data. Okay? So we have each 1 hour, we have the 13 minutes segments. And then for each 13 segments, I can compute the average values after I compute the power spectrum. Okay? And then finally, I need to divide the frequency band width, and I can decide the density. Okay? So, the important things here, again, we have the power, and we have the spectrum. And what the average here? For example, 1 hour segments, we can cut into the 13, 15 minutes segments. And then I can compute the average values, okay, based on the 13 short segments. And finally, in here, I can divided the delta F. The bandwidth is a delta F. Delta F is equal to the total data length over 1. And you can use the capital M, total data number, multiply the sampling interval over 1. Okay, So finally, I divided the delta F, and then I have the density. So again, we know that the power is the P, and the spectrum is the S, and the density is the D. So today, the analyze is, we call that the PSD analyze. So that's why we will have the power spectrum density. OK， 那今天我理论就不多讲，虽然已经讲很多了，但也听不太懂。不过重点就是在你要知道哪来的 power， 那哪里来的 spectrum， 那为什么会有所谓的 density， 就只有这样就好。那我们一直强调 power 就是有二次方就会变 power。那我们一直强调，你本来做完傅立叶转换，你就会有 spectrum amplitude。那为什么最后会跑出一个 density？ 因为你把频宽除回来了，就有一个正规化的概念。它算出来的是这些频宽之下分之多少 power spectrum， 那它就是一个 density 的概念。那为什么要用这个 density？ 你想想，只有密度是不会随着永恒不变嘛？你把我切成2半，我的密度还是会长一样啊。所以唯一只有这样子的方式，你怎么切算出来的物理量还是有代表它本身的意义的。所以你才要算 density。如果你不算 density， 那就会因为你决定的长度不一样，那你算出来的能量就会不一样嘛。所以你要有决定 density 以后，才可以把长的时间窗口切成小段的窗口以后，它还具有本来的物理代表性。如果你没有做这个 density， 那就很奇怪，我时间越长，好像能量就越多，那就好像不太合理。应该是要单位多少之下的这个能量是永远都是固定的。Okay. So the idea is, you should know. Maybe you didn't know the mathematical representation and in details, but we should know what is the power meanings and the spectral meanings and the density meanings. And then in next class we will do analyze. And for the user, we should only adjust the different window lengths, the 1 hour or the 15 minutes for the shorter windows and the longer windows lengths. Okay, so maybe we have a 10 minutes break, and I just emphasize you only need to know what the power, what the spectrum, and what the density, even though you don't know how to compute the answers of the power spectrum density. OK， 好，我们休息一下。